Hello and welcome to our ISTAT Learning Lab of today, Tuesday, September 5th. Welcome to everybody, and I'm very pleased to have with me today Hal Kalamvokis, who is the Director of Aviation Finance at Standard Chartered. Welcome, Kal. Welcome, Hal.
Hi. Thank you very much, Maroon.
Hal has over 25 years of experience in various aviation sectors, including Standard Chartered Bank Analysts or AWAS, with EasyJet and the ANSP Eurocontrol, as well as Airbus and British Aerospace. His role covered strategy, sustainability, aviation finance, market and credit analysis, sustainable aviation fuels, fleet planning, and aircraft evaluation procurement. He is also an ISTAT certified aircraft appraiser and holds an MBA from London Business School and a master's in aeronautical engineering from Imperial College London. Hal will be presenting make a presentation on supporting financial institutions in the aviation net zero transition, plus an overview of the 1.5 degree aligned pathways. So Hal, over to you, and I'll be to the audience members, please don't forget to post your questions in the Q&A button at the bottom of your screen. We'll be taking them up at the end of Hal's presentation.
Okay, is my screen share working?
Yes, very well.
Okay, perfect. Thank you very much for the invitation to do this ISTAT Learning Lab. And I'm just going to start by talking about Standard Chartered's work in sustainability, how that's been brought into the aviation finance team, the importance of net zero, the initiatives we've been working on, and then how we can expect the world to change around us. So Standard Chartered has actually been working in sustainability and focusing on it for many years. It's been part of the task force for climate-related financial disclosures since 2017, and is currently the chair of the Net Zero Banking Alliance. Hard to abate sectors such as aviation, shipping, and automotive were brought into the bank's main sustainability process a bit over 2 years ago. And sort of part of why we got involved in the Aviation Climate Aligned Finance Initiative was in terms of to help ourselves be able to support the bank report on its sustainability. As was in the title, everyone seems to be talking about net zero. Why is it so important? There was an interesting long read article in the Financial Times last month, which actually gave the output of some work that Singapore's GIC had commissioned for it, which is they got potential investors to put together a 60% global equity, 60% bonds portfolio, and then said what happens to returns over the next 40 years, dependent on whether or not climate change happens or how well the response to it. And the baseline on the net zero on the chart in the back on the left is assuming climate change does not happen and we invest in net zero. Obviously, there's misplaced investment, so that depresses returns by about 10%. But then all of the trends we're seeing in climate change would have to stop, and also our understanding of the basic physics would have to be wrong. But if you get a delayed transition, or if the transition, we sort of spend years talking about it and then try and rush, or if it actually fails, the impact on returns is much worse. So as the FT put it, it's the least worst option. Or put it another way, if you're going to make a mistake, investing in net zero is the best mistake you can make. Because if we need to make, if in 10 or 15 years time, we know we need to invest in net zero and we haven't yet done it, it's too late and the impact will be far more negative. This is why a lot of organizations are now focusing on making net zero commitments. Over 550 financial institutions. The Net Zero Banking Alliance has over 130 members. And again, IATA has made a net zero commitment in 2021. ICAO made one last year. And to support that, there's an initiative called the Science Based Targets Initiative, which is already being taken up by many airlines. So this is important to our customers. This is why we're doing it. Just in terms of the requirement for net zero banking signatories, we've got to set targets, we've got to announce them. Priority should be put into significant sectors. Targets should cover scope 1, 2, and 3. And they should be based on scientific scenarios that are 1.5 degree aligned. And so part of our response, and several other banks, is when looking at these requirements, was actually, it's probably better if we work together to try and develop something standard instead of each bank try and do something themselves. And this has already been done in shipping, which is called the Poseidon Principles, which were launched in 2019. So you start with a smaller working group of banks. They don't work in isolation. There are other groups that provide feedback, etc. And then the output is a common methodology that includes a 1.5 degree roadmap and plus whatever data you need to actually run that, so that banks can actually report on the performance of their portfolios. And in terms of scope, this just puts everything in one place, but we'll probably go through most of the things that are in scope in the next few slides, but I just want to touch on what is not in scope. In terms of activity, it excludes military aviation, excludes corporate midget jets, and general aviation. In terms of the emissions, it's the direct fuel burn from the airline operation, plus the upstream refining emissions, which is the most significant scope 3 emission if you're an airline. Yes, sort of airport buildings, ground handling, etc., and aircraft manufacturing, they have scope 3 elements, but they're of an order of magnitude smaller. And on the financial scope, facilitated capital markets are excluded. Secured debt, leasing, and general purpose lending to airlines is included. And in terms of the outcome, there were sort of the 3 bits. One is an agreed and accepted methodology with a defined intensity metric. The key bit, and I'll go into this quite a bit, is the selection of an appropriate roadmap that can be reported against. And then there's the data work piece to be able to support all that functionality, and also make sure this isn't too onerous on either one airline or lessor clients, or actually on the banks themselves and the financial institutions that sign up. Just sort of tackling that last one first on the data. Within NGOs and other bodies that work in the sustainability space, there is a preference for client source data. It's accepted. One might not always get that, and actually in aviation we have the advantages. There are several third-party data providers who have developed emissions calculations tools as well as activity calculation tools that can be checked and validated and be incorporated as part of the plan. And then moving on to roadmaps is, I'd just like to introduce an organization that probably most people haven't heard of, which is the Mission Possible Partnership, who have a link with RMI. And it was really set up to help hard to abate sectors sort of outline what they need to do and how they might approach net zero. There was an aviation transition strategy work piece that was done a bit over a year ago, that including almost 70 participants from many different parts of the aviation ecosystem, in terms of the users, as it were. There are airlines, there are manufacturers, Boeing, Airbus, Embraer, there are fuel providers, startups, there are people who buy business travel, obviously a whole raft of airlines as well, and airports. And this was more about, well, what do we actually think is a credible future for the sector, and how do we think it will reasonably decarbonize, apologies, in the right sort of timescales. And the output of that aviation transition strategy was a decarbonization roadmap, which is one the Aviation Climate Aligned Finance Initiative have selected. And this is sort of the traditional fan chart you see of emissions and emissions abatement. I'll just sort of touch through what all the different elements are. Is sort of at the top, you've actually got the continued improvements, and this includes the current switch that's happening from current technology to new technology, from like CEOs and NGs to MAXs and NEOs. And unfortunately, in the sustainability world, it's been observed that aviation delivers 1 to 2% a year anyway. So that was already put in the bank as incremental improvements that were expected to do. Because those are taken for granted, the additional improvements from very new designs of aircraft and things like that don't appear to deliver as big a slice, but that's because they're over and above what's already happening. And then sort of in the middle, you've got three things that are effectively carriers for renewable electricity, either delivering the electricity direct to the aircraft for battery electric, using electrolysis to turn it into hydrogen, or having made hydrogen, also capturing carbon and combining them together in what's called power to liquid, or an e-fuel. And then at the bottom is what would be called conventional SAFs, which there was a learning lab over the summer on. So I won't go into that much. And then just as a reminder is those bottom segments, they're all drop-in fuels. So they can be used with aircraft that are in the fleet today. We don't have to wait for new aircraft to dissipate through the fleet as time goes by. And in terms of how this is used to come up with a metric for the Aviation Climate Aligned Finance Initiative is you've basically got at the top, that very top line is implied demand, which is assuming an average of 3% growth from when we recover from COVID. This is lower than many publicly quoted numbers for the next 20 years, which are used in marketing. But bear in mind, this is in effect a constrained forecast. We are being constrained by the cost of and availability of carbon. And at the very bottom, you've got the unabated emissions, and you divide the two together to get an emissions intensity metric. But just stepping back is, I told you that was the roadmap selected by the Aviation CAF. Is there were actually 8 that were looked at in significant detail, and then 3 that were down selected to, and I'll just talk through what the other 2 were. The red line here was a scenario for aviation that was come up with by an organization called the One Earth Climate Model. And the blue line is the International Energy Agency, their net zero line, the NZE. These 2 are what are called integrated assessment models, in that they look at the entire global economy and they look at all the segments of humankind's impact on the environment, and they apportion between them. Whereas the Mission Possible Partnership scenario is a bottom-up one. It's sort of being built by the sector of what do we think we can do. As you can see, they're very different. So within the One Earth climate model, they assume very strong growth this decade, and then they assume a very fast switch over to sustainable aviation fuels. So emissions go up very quickly, they go down very quickly. The IENZE assumes demand is effectively rationed to start with. Business travel and flights over 6 hours are restricted to 2019 levels. But that then means in later years, in the 2040s, a higher percentage of fossil fuels remain in the fuel mix. The areas under the curves are about the same. It's all about 20 gigatons of CO2 emitted. And then, as I was saying, we take those two things, the emissions divided by the activity, to come up with an intensity measure. And this is sort of showing the output as it's provided in the Poseidon principles is each participating institution, they basically say how far their portfolio is or isn't away from the line. That's all they say. They don't report, or they don't have to report, their absolute emissions. They don't give any details of the emissions from their clients, and they remain free to set their own targets and decide their own strategy. All it is providing a common measure work framework. And again, is dependent on your business model. You might start closer or further away from the line. So when setting your 2030 target, if you were further away, you specialized in older aircraft, you can say, I still need to improve by 2030 and get closer to the line, but I don't need to be as close to the line of someone whose portfolio only has new aircraft in it, for example. And just sort of touching back to the two leading roadmaps, and this is actually looking at the previous slide was the absolute emissions. This is looking at the emissions intensity, which is the grams of CO2 per RTK. And it's done on a well-to-wake basis. So it's including those upstream emissions from refining, which is in line with NZBA and SBTI guidance. And looking at the 2030 point in these scenarios, there is actually a significant difference, about 20%. And actually in our internal work, the sustainability team in Standard Chartered, they were like, we would like to use the IENZE bank-wide, unless anyone has any objections. And obviously ourselves and shipping went, yeah, we have an issue with that, because at the midpoint, you're effectively trying to meet a target that it's hard to envisage the industry ever meeting, absent significant demand rationing and then airlines putting on fewer, larger, fuller planes, if that makes sense. But what we said is, how credible would it be for us to say, well, in 2030, we're going to be within 35% of the NZE target, or in 2030, we're going to be within 2 to 10% of the MPP prudent target. So that was, again, we could actually use part of the work we were doing with RMI and saying, we actually think we should not set an IE NZE target, but we should actually use the Mission Possible Partnership one. I think more and more institutions that are involved in aviation finance, when they look at this, will probably come to a similar conclusion. And then just sticking with the MPP prudent emissions intensity curve, another thing that was looked at in the working group is, do we actually need differentiating targets for different segments? And this came because within shipping, you can have a 2,000 ton container ship, or you can have a 250,000 ton container ship. And again, is very large cruise carriers and offshore vessels have very different performance. So they ended up actually with 25 different subcategories. And it was looked at in various dimensions of, and there was a worry, would we have to do narrow body, regional jet, wide body? But actually, when you look at it on an RTK basis, passenger aircraft, including any cargo they're carrying, come out relatively similar. but cargo aircraft come out very different. A simple example on this is an A330-300 in a passenger configuration. You can fit about 42 tons of payload on board. If you take all the seats out, convert it into a freighter, you can actually fit 61 tons of air freight in there. The main point is on the main deck, it's much denser. So it's still the same aircraft, but it is delivering more RTK. So that's why you get the green line there for the cargo. And if a counterparty does a mix of the two, you actually calculate where the line should be between them in their proportion. And just sort of making clear, I've sort of talked about well-to-wake and looking at the life cycle emissions. There's what's called the tank-to-wake emissions from burning a ton of kerosene in a jet engine, which generates 3.16 tons of CO2. This is ICAO is the designated competent body under the Paris Climate Agreement, and they just periodically work out what they consider to be the global average is. When you include the emissions related to creating the fuel, that's 3.84. And again, this is the ICAO approved number. And when talking about SAF, I think you're probably all often seen as, oh, well, the emissions are 80% less. That's actually relative to the 3.84 number, not the 3.16, because most of the emissions relating to producing a sustainable aviation fuel actually are happening on the ground in making it. So comparing it to the 3.16 number doesn't really make sense. And there's another point here is that this is actually, if you've got very good eyesight, you'll see that this is CO2e, so which is the equivalent that includes a factor in for things like methane and the other 6 of the gases defined in the Kyoto Protocol. This is not there to try and account for the non-CO2 impact of flights at altitude, primarily because exactly how to do that hasn't yet been agreed by the IPCC, despite certain groups of scientists proposing ideas to them for more than 20 years, because the challenge with those non-CO2 effects is a simple multiplier doesn't work, because it gets driven by the time period you choose. You often hear a 3 times multiplier spoken about, but that's actually looking at the historic emissions from aviation. So it's comparing flights today and their non-CO2 emissions, like say NOx and persistent contrails, with the CO2 impact of flights that happened 2 or 3 decades ago. And the other non-CO2 impacts have actually already died down by that. In contrast, if you go have a forward-looking view, many CO2Es are done on the 100-year scale. If you try and do a 100-year CO2E for the non-CO2 impacts, you come up with a number that's about 10%, i.e. 0.1. But that's because you're just looking at the CO2 emitted today, which will carry on impacting the environment for every single one of those 100 years, and then several other impacts that will only happen this year, and it'll take a decade or two for the perturbation of the atmosphere to die down. Just in terms of going on to as we go into what else is going on in the industry, I'm going to add in here the emissions from different sorts of hydrogen, which was actually quite a challenge to get the information from. And grey hydrogen is the predominant source that's made from natural gas. Blue hydrogen is similar, but you've used carbon capture to try and capture ideally more than 90% of the CO2 emissions from hydrogen's production. First point is these bars are higher, but the energy per kilo, because these are the CO2 per weight, it's actually better for hydrogen. So you don't need as much. But we'll look at that a little bit further going on. And I'm now going to step into IATA's net zero roadmaps that were issued about a month or two ago, which there are 6 of. As an ISTAT appraiser, obviously the aircraft technology roadmap is the most interesting, but one has to look at the energy and new fuels one as well. And again, is the operations and the other roadmaps are sort of beyond the scope of the Learning Lab today. And to their credit, IATA have done a lot of work on this, and a lot of it is they're putting if you want to do X by this year, you had to have already done Y 5 years beforehand. And even as summaries, they're very hard to read. So I'm just going to distill down a few of the most pertinent points. So they've got sort of two streams here on the aircraft technology one, the reducing in-flight energy, just making every aircraft more efficient, or new aircraft more efficient. And then they have a change the fuel sort of roadmap that I've added in some from the energy and new fuels. Those two key bits sort of in the middle there, which is we need standards for the aircraft airport interface and what is and isn't approved equipment to pass liquid hydrogen from wherever it is on the ground to the aircraft. And there's also a work stream which is titled hydrogen refueling exclusion zone defined. Now, hopefully they go, well, actually, we don't need a exclusion zone. But the people who determine safety of fuel handling on the ground have to work through a process. Normally, the outcome would be an ISO, an international standard, on how you do it safely. The boxes in red are all to do with sustainable aviation fuels, which again I won't go through as they've been in other learning labs. And then I'll just sort of point out with even the sub boxes I've chosen, the sort of the work that's already underway or planned. So that flight test of an ultra high aspect ratio wing, that's a NASA X66A program. And then this mild hybrid turboprop is what ATR are proposing as the EVO. Now, at the moment, Boeing are proposing something in terms of a new narrow-body aircraft for entry into service 2035. It was interesting at the Paris Air Show, the mood music from Airbus was more, yes, well, if they're doing that, don't worry, we'll react. But there's nothing public at the moment, whereas their previous sort of public information is on what I've called there's a 95-seat aircraft and there's a sub 200-seat aircraft, which I've just given labels to so we can talk about them later. And just going back to, if you remember, that middle wedge of the fan chart is you've got renewable electricity. How do you turn it into productive work? Now, aircraft that are 100% battery powered will always remain a small element just because of the weight of the batteries. And even if you assume the levels of battery technology improvement that are programmed, they still end up being quite small aircraft that are responsible for a very low proportion of the emissions today. Hybrid electric could actually deliver more decarbonization. We'll touch on that as that. So on here, we've got the blue line at the bottom is power to liquid. That's e-fuels, where you've taken the hydrogen and you've combined it with captured carbon. And then you've got the bounds for what hydrogen could be. This is from the ATAG Waypoint 2050 document, which if you haven't read, I'd recommend, as it's a very good starter point in terms of aviation sustainability, because they've tried to bring everything into one place and describe how it fits together. Now, within that, ATAG are taking the IENZE renewable hydrogen costs, and they're adding about $1,200 a ton to it for the distribution and liquefaction, etc. And again, bear in mind, the hydrogen looks more expensive, but we're talking per weight here. But sort of talking to the people in the fuel supply industry and who are developing sustainable aviation fuels today is several of the opinion of the ATAG's assumption on shipping costs for hydrogen were a bit low. And I think effectively ATAG are assuming an average, and that at many airports where liquid hydrogen is used, it's produced locally. So this chart is basically showing, and again, is it's per ton, is the cost of moving a ton of SAF or power to liquid around the world in the green line, and the cost of moving liquid hydrogen equivalent distances. These are shipping costs, moving them by sea. And the point is here is there are lots of projections on the cost of fuels and the cost of electricity, but bear in mind, we end up paying the price, which may not be related to it. Simple example if you look at, say, Abu Dhabi Airport, major oil producer, they sort of make it round the corner. The cost of getting a ton of kerosene to the airport is probably between $50 and $100. Its price 2 weeks ago was $950 a ton. So a lot of when you look at projections for the falling cost of sustainable aviation fuel, of hydrogen, etc., one of the assumptions there is places with a lot of renewable energy potential, but very little demand, are exploited to actually get low cost renewable electricity. A good example of this is the Porsche have come up with a product for people who buy new 911s. If you're worried about the environment, they will supply you with e-fuel. And this is actually made in Patagonia. The reason there is they have some of the strongest, most consistent winds anywhere on land. So it's a very cheap place to make an e-fuel. And also, they're doing it in places where there's no other industry, no one lives there. There wouldn't be another off-taker who would bid up the price of their electricity. Now just stepping through, sort of just showing some pictures of aircraft, because an ISTAT presentation wouldn't be the same without them, of the different things I highlighted in the ISTAT roadmap. And sort of starting at the smallest first, this is the ATR, what they've called the EVO. They delayed the launch decision recently, but they're still targeting an EIS for 2030. Will that slip? Maybe not. Key point here is it's hybrid electric. They're targeting 20% fuel burn reduction. About 10% of that is coming from the propeller, a new propeller. 10% of that is coming from the hybrid electric system. Because what that's really doing is, on takeoff, it's providing a small boost. So the actual engine can be smaller and sized for cruise, and then it burns less fuel in the rest of the flight cycle. And one would expect this technology to diffuse through to regional jets, narrow bodies, etc. And then stepping into the regional space, Airbus has been talking about a 95-seat aircraft, less than 100 nautical mile range, which is actually a turboprop. And they've been looking at 2 different ideas to achieve this. One can be done, the technology will be mature sooner, which is you still have a combustion engine and you burn the hydrogen, which could be available in 2035. But as you're burning the hydrogen, the key point is it's not zero emission. You still have some NOx. It's sort of interesting to understand, compared to today's jet engines, how that would look. Rolls-Royce recently did a test on a small engine running it off compressed hydrogen, and the NOx was as expected. The key point is it's not zero. The aircraft on the bottom is actually using hydrogen fuel cells, which has the, if you can get the technology right and you can get the size and the weight right, it has a greater efficiency. And because you're not burning the hydrogen, you don't have issues with NOx. And as a proponent of this technology also explained to me, I'm not too sure how significant it is part of the particulate matter you're getting out of an engine is actually coming from the oil and the seals. So even in a hydrogen engine, you'll still have a tiny amount of that. And the other advantage, because in this concept, there are 6 engines, 6 small liquid hydrogen tanks. They're not taking up space for payload in the fuselage. When you think of in terms of investability of projects, one question is, do you need to do the first aircraft to develop the second one at a later date? Because probably fuel cell technology will only be at the level of maturity, maybe, I don't know, 2045 onwards. So does the first aircraft end up with a very short production life? Or do you have to do the first one anyway to have learned enough about handling liquid hydrogen, etc., to do the second aircraft? And in terms of trying to look at what might be the potential demand and hence abatement potential for an aircraft of this size, I sort of just looked at current 95-seat aircraft and just actually said, how significant is this market? On the left is just data pulls from Cirium. One is from 10 years ago and one is today, of basically 70+ seat regional aircraft, that is, which I've just taken as 4 or 5 abreast aircraft. You have in some of these side categories, you'd have the smallest versions of the A320 and the 737, but most people selected those as an add-on to the larger aircraft, so they wouldn't really be natural things you'd replace with a 95-seater. In terms of the total in-service and on-order aircraft, the population has grown by about 20% in 10 years. That's good. But what seems to be happening is it's hollowing out. There's been growth in turboprops, and the turboprop number would be better. But at the moment, there are quite a lot of dash Q400s and a few ATR 72s in storage that might come back into the fleet soon. The 70 to 79 bracket, 70 to 89 bracket, apology. These are all single class. The most of those are what would be called a scope clause aircraft, i.e. they can be operated by the regional airlines in the US. Even though normally the scope clause is 76 seats 2 class, and it has an MTOW limit as well. So they've grown. The middle size has actually shrunk a bit, and then there's been lots of growth in the bigger size, which is now the A220-300 and the E195 E2, which is actually a stretch of the original E195. And I also looked at how important in this sector might family considerations being. And it turns out that of the Embraer E-jets in service, the sort of 1,700 of them, only about 20% of them by aircraft number are with operators that operate multiple sizes. Almost half of the aircraft are operated by fewer, and they're often very larger carriers who are providing those scope clause services in the US. Only about 20% are in that mid-size, that are something around 90 seat. And actually looking at it, often these are operators that only have very few aircraft. It's almost half of the E-jet operators are actually in that segment. So it's an interesting area. It's hard to understand how big an impact it would have. But then I think part of the question in terms of looking at green hydrogen pathways is, does it, is it an important first step that has to be made? Going on quickly into narrow bodies this is the NASA X-66A, which they've agreed a program with Boeing on. It's actually the fuselage comes from and tail comes from a MD-90, which gets chopped up and moved around. The aim is in 2028 to fly it with a Pratt & Whitney GTF, and then a year later with CFM's open fan. When Boeing were first promoting the Sustainable Flight Demonstrator, they were talking about a 30% fuel burn reduction compared to the MAX. You'd expect that to be better with the open fan, but we'll watch this space. And this links up to picture on the left, which is Boeing's proposal for the their new SFD. Sorry, there's a typo there. That's 2035, not 2025. Airbus has been talking in public about their hydrogen aircraft, less than 200 seats, less than 2,000 nautical miles. But the key point at the moment is that's a single point design. Boeing is talking about a family of aircraft. They've shown two, there could be three, where you're using the same cockpit, etc. systems to cover different sizes. And the importance of that is, I'll just show by looking at where emissions come from today in narrow bodies. Here you've got the three different colors are green is the medium segment, A320s, 800s, MAX 8s. Then you've got large in gray, small A319s, 737, 700s in blue. And if you say Airbus's hydrogen proposal, it won't cover every single sector because it's got a range limitation, but it would also be able to, of airlines upsizing from small, be able to capture then. It could actually cover about not quite 60% of narrow body emissions. But if we roll forward to 2036, which could be an entry into service date, that's dropped closer to 45%. And you can actually see the increase in the number of large narrow body aircraft in the fleet and how they contribute to emissions. And also the small segment is largely being eaten out to the people who want a specific tool, be it a MAX 7, be it an A319 or an A330-300. So a single point design, one wouldn't expect to have as great a market share. And it's something in terms of appraisal methodology, most appraisers would actually look at that going, is it part of a successful family? And just to sort of bring home what we're talking about on the narrow body side in terms of families is, here is just, and I've recycled this from something else, is what could be the all economy seating layouts. And just starting at the bottom, this is sort of 197 seat high density. This is, or it certainly should be, what Boeing are calling the VS1, their smaller new aircraft. Actually, the top aircraft is the largest narrow body you could do, which is really a 757-300. And that's sort of showing that to fit the hydrogen tanks in the fuselage, you're coming up with an aircraft that has the fuselage of a 757, the payload of a 737, and the range of a 717, which is naturally compromised compared to the thing on the bottom, which would be a clean sheet design optimized for that size group. So the hydrogen aircraft would be heavier. You would normally expect, all other things being equal, it to have a higher thrust engine. So that means more fuel, which then you then combine out and saying, okay, I needed less weight of it, but have I actually ended up in cost-wise at the same place, or actually better or worse? And just concluding up the presentation now to leave plenty of time for conversations is on the technology and fuel roadmaps. I haven't spoken about it, but the SAF part of the decarbonization puzzle is very important. It's also very important for current asset owners, because that's actually how we keep and extend the life of the aircraft being built today. The manufacturers are now talking about narrow-body replacement sometime they're talking middle of next decade, but it might be a bit later on. That shouldn't scare us, because by 2036, the Neo will have been in service for 20 years, which is as long as the NG was in service before its replacement came. And just the last picture there is something that we need to spend a lot of time as an industry looking at, is how do we integrate engines and airframes better, and how do we generate lift better? And then finalizing up on going back to where I started from, on the conclusions from the Aviation Climate Aligned Finance Working Group, is we've got to the stage where the overall plan and idea is settled. The documentation that would be used for financial institutions to join the program and it to be constituted are being worked on. And so now RMI and the working group banks are actually looking for, are there other financial institutions that would be interested in joining with the full launch, which is scheduled for January 2024. We naturally think there are many benefits of it. And if anyone's interested, the contact details of the various people in RMI are on the right if you want to follow it up with them. So that is the end of my presentation. Shall we go to Q&A now?
Yes, thank you very much, Hal, for all this very informative and precious information. To the audience, the presentation, the slides that Hal just went through will be available on the ISTAT website later on. Yeah, we have a couple of questions. The first one, I think I know who asked it, but on regarding the CAF methodology, if the focus is on carbon intensity, does that mean that CAF aligned banks will increasingly lean towards higher density LCC lending and see low density seating aircraft such as full service carriers less favorably?
It's more complicated than that on two aspects. Is one, because the metric is per RTK and not RPK, it then means the difference between, say, an A321 in a 240-seat layout and an A330 Neo in either a high density or a multi-class layout is, it actually starts to narrow up. But the other thing is as we're including the percentage of SAF usage as well in calculating it. So if you look over the next, say, 10 years, that could well be more important than actually the seating density on aircraft. So for an example, Southwest, Ryanair, and Wizz have all made SAF commitments of the order of 10% by 2030. EasyJet has yet to make one. So you might see there could well be more differentiation between clients in terms of how well progressed they are on SAF uptake, as opposed to saying, well, actually, I want my portfolio will look better with airlines in charter configurations or things like that. Kind of the other point there is it also depends what's in your portfolio today. So if you've got more of a diverse mix, you're probably going to work with those clients to help decarbonize on the way, if that answers the question.
Thanks, thanks for that. Another question just on Jet Zero. I'm not sure if what does that question refer to. I've heard of Jet Zero, but what's you want to take this one?
Yeah, sure. I assume the questioner is relating to Jet Zero, which are a startup proposing a blended wing body concept. which, again, going back to the IATA roadmaps, the validation work is in there, but the actual decarbonization increment you would see from developing it is not so apparent. I mean, there are two key things to remember here is that initially what was proposed decades ago was a flying wing. And the first proponent was Frank Northrop for strategic bombers. And his thought was it's a more efficient way to package the payload and everything you need. Because something like a B-52, it has lots of empty space in the fuselage. Also, Frank Northrop spotted that the stability requirements for strategic bombers were different than from transport aircraft. So he was saying the flying wing has less wetted area, so it has less parasitic drag, so it's more efficient. Interestingly enough, Jet Zero have sort of gone through the outside and other side, and when they're talking to journalists, they sort of said, yeah, well, a flying wing is actually an extreme version of a blended wing body aircraft. If you look at their proposal, they're saying they're going to save fuel burn by predominantly not having tail surfaces. So their argument is their design is fundamentally stable, so it doesn't need them. But when you look, but you've also got to bear in mind their reference aircraft is a 767. So when they say we're going to burn 50% less fuel than the aircraft it's designed to replace, yeah, that's a 767. But if you look at the technology that went into a 787, and Boeing has actually did presentations about this at the time, is if you applied that to something with the same fuselage cross section, the same payload range as a 767, you just did a straight replacement, they could have saved 40% in 2007. Obviously, a 787 is you've got a wider fuselage, you've got more cargo space, it goes faster, you've got a better cabin altitude, you've got larger windows. So they traded lots of things to make a more productive airline for aircraft for the airlines. But so going back to Jet Zero, I struggle to understand how it improves compared to anything else you can do. Also, I struggle to see how it gets certified as a former certification engineer and safety manager, is that, yes, they've made the statement, it's stable, we don't need a tail, but that's, okay, you're going to have to do lots of flight tests to prove to the FAA it never stalls. It's impossible to go into a flat spin. And also, it only has two engines. So when they lose an engine, how does it fly in a straight line? So on those sides there are proponents for blended wing bodies, but and the other compromise with them is one of the main reasons why transport aircraft are long thin tubes is it's a very efficient pressure vessel. And in the work that was done before the Neo and the Max were launched, is Airbus had what was called the A300X program. Boeing was looking at the 737 replacement study. While I was at EasyJet, we were on both of the advisory boards. And one of the manufacturers, they actually looked at, well, what if we have a 250-seat aircraft and we have it in a conventional tube, or we do a blended wing body? Making it into a smaller sort of box adds about 5 tons to the weight of the pressure vessel. This is on an aircraft with a payload of 25 tons and an operating weight empty of about 5 tons. So blended wing body aircraft, they solve one problem, but it's not clear they don't add in other compromises that actually mean there are ways that are easier to certify as passenger transport aircraft. That is actually the way most manufacturers will go.
Thanks for that. Now, clearly, we see the engineer speaking here, and it's a very, very interesting and very valuable information. We have Philip asking a question about the supersonic, so blended wing aircraft. So, what, if any, impact will the introduction of a supersonic blended wing aircraft have? Have they been considered? So,
Well, I think that's probably two questions, and we've just answered the blended wing bit.
yes, correct.
But again, is another startup that's making lots of noise in the industry's boom supersonic is
Yeah,
the answer to this question is that in effect, you can't find the part of even the IENZE or anyone's emissions roadmap for the future of commercial aviation that's allocated to supersonic travel. In part, there's that question of when is it actually going to happen, and how significant would it be? The challenge with boom is that when you look at it, the aircraft is about the same size as the Concorde, certainly in terms of cabin. And I think what they're hoping to do is offer people more space, and people may pay more for it. But it's not clear that an aircraft that flies slower, so yes, it takes you 3.5 hours to get to New York from London, but it takes you 7 hours to get to Chicago. So exactly whether or not that aircraft is ever going to be certified, whether it is ever going to carry any passengers in revenue flight. The flip side, Boom have said, oh, don't worry, everyone who operates it will buy 100% SAF. But flying faster than the speed of sound is more energy intensive. That SAF you took away from multiple other air travelers.
correct.
But the straight answer to the question is they're not really considered because people just can't understand whether or not it's going to be significant. And just one thing now I remember is if you look back and read the books and the history of Concorde, the biggest environmental opposition to it, over and above local airport noise, was actually the destruction of the ozone layer, which actually we now know also has a climate impact. So ironically, if as it becomes more real and successful, people are going to look at things like this harder. So you'd wonder how many people who are concerned about net zero, who are concerned about sustainable aviation, will actually be associated with that.
No, indeed, it's supersonic travel has always been one of the great adventures of humankind. But I think in the current environment and as you say, I mean, there's very little SAF to go around as it is. Having reserving it for supersonic, I think there'll be a lot of issues and negative press around that. I think that's all the questions we have, Hal. Thank you very much for all your inputs, and as I said, very valuable information all around. I mean, this is certainly a subject that will remain with us for some time, and it's just important that we see how banks and data are measured up and used to support our transition. And clearly, from your first slide, it's in all our interest in not only humanitarian but certainly economic interest to look very, very strongly at this and transition towards a net zero. So with this, thank you, Hal, for your time and your contributions, and to the audience, thank you for attending. We'll be back shortly with another learning lab. In the meantime, you'll have Hal's presentation on the website shortly. Thank you very much.
Thank you and goodbye.
Bye-bye.